So how do I do that? How does this work for instances like B? Well, what I want to do is when I look at a situation where I have, again, a rational expression, you really can't plug infinity in. However, what I can do is when I see, well, I have different powers of x. And what I do is I look at the top and bottom and see what the highest power of x is. And in this case, x squared is the highest power of x. And both the numerator and denominator have it. So what I do is I divide each term by that highest power of x. So essentially I'm going to be doing 1 over x squared being multiplied to the top and 1 over x squared being multiplied to the bottom. Or dividing the top and bottom respectively by x squared. I'm not changing the value here because I am still essentially multiplying by 1. But when I do that, I get 3 minus 4 over x plus 9 over x squared over 2 plus 5 over x minus 3 over x squared. Now that I have a bunch of fractions over some power of x, as x approaches infinity, each one of those becomes 0. So, in this instance here, as x approaches infinity, the 4 over x, the 9 over x squared, the 5 over x, and the 3 over x squared all became zeros. So essentially I have 3 minus 0 plus 0 on top, I have 2 plus 0 minus 0 on the bottom, and that gives me 3 over 2 as a final answer. So the limit as x approaches infinity of that original function is 3 halves. And I do the same thing every time I come up with a situation like this, okay? Now when I look at C, the highest power of x that I see on both the top and bottom is x cubed. So I'm going to divide essentially all the terms by x cubed. Or in other words, multiply the top and bottom by 1 over x cubed. And when I do that, I get on the top I get 5 over x minus 6 over x squared plus 7 over x cubed. On the bottom I get 4 minus 5 over x minus 8 over x squared plus 1 over x cubed. The other thing I also want to point out as I go through all of these, and hopefully you've been noticing it, that, a lot of students sometimes get a little too lazy when they deal with limits because they don't want to have to write LIM, X arrow, and some number or infinity symbol over and over again. The problem is, when students get rid of that, sometimes they forget to evaluate the limit when all is said and done. I've seen it more times than I would care to like to see it. So my advice to you is, even though it seems to be a little bit tedious to rewrite limit, until you actually evaluate the limit, until you actually use a limit rule to establish something or come up with some values, keep writing it until you actually evaluate the limit. Because here, as x approaches negative infinity, now, again, it doesn't matter if x is positive or negative. I mean, as I approach an infinitely big number or an infinitely negative number, anything over x here is going to go to 0. So I get 0 minus 0 plus 0 on top. I have 4 minus 0 plus 0 on bottom, which gives me 0 over 4, which is 0. Do the same thing with D. Again, if I'm approaching infinity, I want to get some of these numbers over x's or some power of x. So I look at the highest power of x that I see, which is an x squared. So I divide the top and bottom each by x squared. I end up getting 4 plus 3 over x minus 2 over x squared on top. And I get 1 over x plus 5 over x squared on the bottom. Now I'm able to evaluate the limit because each of these, the number 4 is not going to be affected because there's no x term anymore. The 3 over x, the 2 over x squared, the 1 over x, the 5 over x squared all become zeros, which gives me 4 over 0. Now it's a different issue now. Now I have 4 over 0, which means that I have a choice that this is either going to approach infinity or negative infinity. Now the thing is, some students get a little confused here because they say, well, what about does not exist? Well, remember, does not exist is only an option for a two-sided limit. If I'm approaching infinity or if I'm approaching negative infinity, it is a one-sided limit. Think about it. I'm approaching infinity, which means I go on forever and ever and ever. I cannot approach infinity from the right. That means I have to have gone beyond infinity, and approach from the right-hand side. Well, I can't do that. I can't go beyond infinity. Only Buzz Lightyear can, or maybe Chuck Norris. Yeah, he's kind of doing infinity twice. So, old joke. So, it's automatically considered to be a one-sided limit. So it's going to be a 50-50 choice here. So I got to look at the situation I have here. As x gets infinitely big, going back to the original thing, x plus 5 on the bottom is going to remain positive. So 4 over the x plus, or this thing over x plus 5 is going to be a positive result. So that means I'm going to get the answer of infinity. Going back to these results here, how does this relate to things we've talked about before involving rational functions? Because remember, we've already talked about how we've connected the holes, how we connected the vertical asymptotes. Anytime you're doing a limit as x approaches infinity or negative infinity, you're actually looking for a horizontal asymptote. If you want to look for a complete horizontal asymptote, you should really be looking as x approaches infinity and x approaches negative infinity. But 9 times out of 10, unless you start getting involved with exponential and logarithmic functions, you're typically going to have, the same result either way. If you're just looking at a purely rational function, it's going to be the same result either way. Other functions, not so much, because some functions like exponentials and logarithms will have a horizontal asymptote one direction, but in the other direction it doesn't behave like a horizontal asymptote. So when I look at the situations like, A, B, and C, those told us that we had a horizontal asymptote, okay? Because they kind of go along with the rules, because like in A and C, I have the highest power of x in the denominator, and if you remember the rule for that, that told me that if I had a rational function, the highest power of x is in the denominator, then y equals 0 was your horizontal asymptote. When I had a rational function where the power of x, the highest degree of x, was the same on the top and bottom, that meant that I would take a ratio of the leading coefficients, in this case the 3 over 2. And that's why that works. When I have a situation like D, when I had the highest power of x in the numerator, and the result of that is that I end up getting either infinity or negative infinity, depending on the situation, that was the existence of an oblique asymptote. Either, for us it was a slanted line, but other shapes for oblique asymptotes can actually exist. So that's how you could tell the same thing using limits. So these use of limits can tell us the exact same information that all those rules taught us back in units 2 and 3, or I think more so unit 2. Yeah, unit 2, when we were talking about rational functions and finding these particular characteristics of those graphs. So the limits are a way of telling the exact same thing. And as a matter of fact, those rules that I had discussed in chapter 2 actually come from these limit values and how they occur.